theory type question from a textbook by a gentleman by the name of Underwood Dudley. This was published way back in 1978. I think it's a great book, fantastic book. It's section 4 in the book, problem 11. And you're supposed to find a missing digit here. Now, folks, of course, armed with a calculator, you could multiply all this out. You can see 3 times 5 is 15. So you suspect maybe this number is right. It's a 5-digit number times another 5-digit number. And again, if you multiply this out by hand, you know, you could eventually figure out what D was, right? Just by eyeballing the fifth position, I guess. However, we want to look at a so-called more elegant way of doing things. We're dealing with what they call congruence arithmetic or modular arithmetic. Notice this equal sign gets replaced with a congruence. The reason is if something's equal to itself, then its difference is equal to 0, and any number divides 0. That's what modular arithmetic means. It means 9 divides the difference of what's on the left and right hand side of the congruence symbol. Okay, but the way to remember it is just you can treat equality and congruence in much the same way. Now, it turns out there's a very special result here that's going to help us out quite a bit. It's nice to remember what the decimal expansion actually is. Okay, this means exactly what it says. It's all the digits times successive powers of 10, right? Now, it turns out, and I'm just picking it, the same thing holds for this. I'm just using this guy right here as an example. Notice that you can replace 314,000, or what is this? 31,415. It's congruent to the sum of its digits modulo 9 because 10 raised to the 9th power is just equal to 1. And just think of it as equality, right? You see, this 10 to the 4th just went away right here. This 10 to the 3rd went away right here. This 10 squared also went away. It's just equal to 1. See, and so all of a sudden you can write down this congruence, and you're just doing simple addition right here. And it's because of this truth. 10 to the n is congruent to 1 mod 9. Now, just a simple example would be 10 squared right here. 10 squared minus 1 equals to 99, which is certainly a multiple of 9. Okay, and really these two statements are considered to be equivalent. 10 to the n minus 1 is divisible by 9. This is another way to write it. Okay, so that's really what it means. It's not like you really have to think about that arithmetic every time, but this wouldn't change if this were 10 cubed, 10 to the 4th, you know. So that's why we got away with this. In the very same fashion, we got away with this statement right down here. Now, you may be wondering, how did we reduce this to 7? Well, another nice truth right here is that 9 is congruent to 0. 9 is congruent to 0 mod 9. Sometimes people leave this out when that's the understood moduli. But notice what happens right here is that we have 5, let's see, we have a 9 here, which would become 0, right? And what else do we have here? Do we have anything else that will become 9? Yeah, we have a 6 and a 3 that is 9. You see, so this 9 would become 0, 6 plus 3 would become 0, and all you're left with is 5 plus 2, which is 7. Okay, that's 7 that you see right there, right? Okay, and in a similar fashion, we got 5 right up here, okay? So that's where this 5 times 7 comes from. Okay, 5 times 7 comes from that statement. But now the right-hand side also has the same kind of thing going on. You can just sum up its digits, right? And the rest of this, folks, is just essentially arithmetic. 5 times 7, if you divide it by 9, you get a remainder of 8. And you can verify that, folks. If you multiply 5 times 7, you get 35, and you divide that by 9, and you do get a remainder of 8 right here. Okay, now the rest of this is just simplifying. What do we have going on right here? 8 stays on the left-hand side. We have a ton of 9s that went away. All of these 9s, this 9, this 9, and this 9, and this 9 are all 0, right? Okay, and then so you end up with this statement right here. And one more time, you have 5 plus 3 plus 1, which is congruent. That's 9, which is congruent to 0. So what you get right here, folks, is actually 6 is congruent to D mod 9. Okay, and so that tells that there's what they call a reduced congruence class. You have 0, 1, 2, 3, 4, 5, 6, 7, 8 for modulo 9. And so 6 is the only choice, and it's the smallest choice. It also has to happen to be a decimal digit. And so the answer is D equals 6. Okay, let me circle that, folks. Now you may be saying to yourself, you know, I could have multiplied that out. You went through all of that tirade about why this is true. And you probably could have. You could have multiplied this out by hand and discovered that D was equal to 6. But imagine a much larger number, like let's say you have 20-digit numbers. Okay, I don't think anybody would enjoy that task of multiplying out a couple of 20-digit numbers. And again, I'm trying to explain it here and slowing you down a little bit. You could probably just read this and follow along and get the answer. But anyway, D equals to 6 is in contrast